Okay, here we are in the last section, and that's logarithms and pH. It turns out that a lot of things that we experience or that we perceive are actually on a logarithmic scale, which means it makes a lot more sense for us to talk about the log of the what's going on instead of directly what's going on. It brings it more into terms that we can understand it. Some examples of that, well, pH we're going to talk about in a bit, but decibels, when we're talking about sound, that's also a logarithmic scale. So the decibel is defined as the log of the energy in the sound. Richter scale, so when we talk about earthquakes, that's also a logarithmic scale. So the Richter number is actually the log of the energy in the earthquake. Likewise, when we're talking about pH, it's actually the log of the number of hydrogen ions in the solution. And it's actually the log of 1 over the number of hydrogen ions, and that's just how it's defined. So these formulas we're going to need to know, and a couple other ones for pOH, which is very, very similar. It's almost the same thing. So in a liquid, in water, the Molar concentration of hydrogen ions can range from, generally, on the low end, we can have 1 times 10 to the, well, let's go on the high end. 1 times 10 to the 0, which is equal to 1 moles per liter. So that is about the most that we can ever see in water. And then on the low end, so the smallest concentration we would typically see of hydrogen ions in water is 1 times 10 to the minus 14. Now, the pH scale isn't absolutely between 0 and 14. There's no upper or lower bound. There are things with pH less than 0, and there are things with pH more than 14. But for our intents and purposes in this course, we're not going to worry about those. So the pH of a solution is defined to be the log of 1 over the molar concentration of hydrogen ions. So according to this formula right up here. So if I have something that has a lot of hydrogen ions, it's going to be very, very acidic. And the pH I can calculate by taking the log of 1 over that number. Now, there's a law of logarithms, a rule of logarithms, that tells us that the log of 1 over x is equal to negative the log of x. Now that's just a property of logarithms. It is mathematically provable, but we're not going to do that in this class. But I would like you to verify this. So I'll give you an example. Let's say I'll do 1 divide by 25, so that's 1 over 25, and then take the log of that. Notice it's negative 1.4. So that was 1 over 25. So what if I take the log of 25? Well, I get 1.4. So it's exactly like predicted. 1 over 25, if I take the negative of that, it's 1.4, which is the log of 25. Okay, so that's one example. It's not, or it shouldn't prove to you that this law is true, but this is a mathematically provable law, and we're just going to use it. You should do a few more checks on that just to verify it for yourself, and if you're interested, you could look up the proof of that on YouTube, I'm sure, or ask me and I'll talk to you about it. Anyways, so we know this, so we're going to use that. So the pH is equal to the log of 1 over the hydrogen ion concentration, which is equal to the negative of the log of, now 1 times 10 to the 0. Okay, these are base 10 logs, so 10 to the 0, the log of 10 to the 0 is just 0. So pH equals -0, which is just 0, right? So that's the most acidic thing that I can have in a normal water solution. Likewise, if I go over here, the pH of the most basic thing I can have is the log of 1 over 1 times 10 to the -14. Okay, and I'm going to use that same rule. I know that that's equal to the negative of the log of 1 times 10 to the -14. And I know from my logs that 1 times 10 to the -14 is just 10 to the -14. And the log of 10 to the -14 is -14. So the pH of that is negative -14. And I have a negative negative, which becomes a positive. So it's 14. So here I have my pH scale goes from 0 to 14, 0 being the most acidic and 14 being the most basic. And right in the middle, and normal water at equilibrium is right in the middle with a pH of 7, which to us seems balanced. And most things that are comfortable to us are a pH around 7. If we come in contact with something significantly less or significantly more, it's going to irritate us. Okay, that's the pH scale. Now we're going to talk about the OH scale. Now remember, we have this formula from before that relates OH and pH, and that's H, my molar concentration of hydrogen ions, times OH, my molar concentration of hydroxyl ions, always equals 1 times 10 to the -14. So the pOH is defined exactly the same way as the pH is. It's just the log of 1 over the OH, the molar concentration. And again, we're going to use that same rule that the log of 1 over x is equal to the negative log of x. So pOH is equal to the negative log of the molar concentration of OH. Now, remember our pH scale goes from 0 to 14. Now, a pH of 0 corresponds to, we get a pH of 0 when our molar concentration of H is equal to 1 mole per liter. Okay? And I know from my formula up here that if I have an H equal to 1, then my OH, so H is 1, and OH is then going to be equal to, well, I know from my formula that 1 times OH has to equal 1 times 10 to the -14. Divide both sides by 1, and I have an OH is simply 1 times 10 to the -14. And I've written that. I don't like the way I've written this. I just want to fix this here. Because really what I'm saying is when my pH, oops, not that. When my pH equals 0, then my H is equal to 1 mole per liter, and we saw that just in the last slide. Okay, so, and then I use this formula up here that we used last section to say that when my molar concentration of hydrogen ions, this H plus, is 1, then my OH is 1 times 10 to the negative 14. So where pH is 0, POH, and let's just do this, POH is equal to, again, the negative log of the molar concentration of hydroxyl ions. Oops, that's a minus. I always want to put a minus 1 there for some reason. So POH is equal to the negative log of 1 times 10 to the minus 14. Remember, 10 to the minus 14 corresponds to this pH of 0, where H is 1. And from this formula here, if H is 1, then OH is 1 times 10 to the negative 14. So the negative of the log of 10 to the minus 14 is just 14. Remember, we saw this before. The log of minus 10 to the minus 14 is minus 14. The negative of that is 14. So when the pH is 0, the POH is 14. Okay, so let's see what happens when my on the other end. So if my pH is equal to 14, well, we just saw that corresponds. That means that my molar concentration of hydrogen ions equals 1 times 10 to the minus 14. And you can just rewind this video to the start if you don't remember doing that, but we just did that. Okay, so again, by this formula that we used a whole bunch in the last section, that means then that my OH must be equal to 1. And you can calculate that. You could do that as an exercise. We've done practice problems where we've done this. So it's just using this formula. If H plus is 1 times 10 to the 14, then OH minus has to be 1. Okay, if OH minus is equal to 1, then I know that my POH is equal to the negative of the log of my OH. So my POH is just going to be equal to negative of the log of 1. And I'm going to write 1 as 10 to the 0 because it's a little bit easier to see. I know that log of 1, or log of 10 to the 0, is just 0. And negative 0 is the same thing as 0, so we'll just write it as 0. So I've gone from this pH of 14. If the pH is 14, I know what my molar concentration of hydrogen ions is. If I know what my molar concentration of hydrogen ions is, I can use this formula here to calculate my molar concentration of hydroxyl ions, and then I use my hydroxyl ions, the OH, concentration of OH, molar concentration, to calculate the POH. And when the pH is 14, the POH is 0. So this POH scale is just the opposite of the pH scale. And something that, a formula that we're given in the book that we can, I guess, probably notice from here is that if I do a few examples, I'll find, and this is actually a provable formula, that my pH plus my POH is always going to equal 14. Now look, this formula is actually the exact same formula as this one. These are the same. It's just the first one is expressed in the relationship of hydrogen ion in molar concentration. The second one is expressed in the log scale of molar concentration. So one of the things I'd like you to notice is that when we move it into the log scale, up this multiplication becomes addition. And here this exponent just becomes a number. So that's one of the nice things about using logarithmic scales, is it takes multiplication and makes it into addition. And this is actually, I don't know if any of you guys have ever seen or heard of slide rules. It's before calculators. I think I have one here, actually. I do. Before calculators, people used to use these things called slide rules to do math. And these are based on logarithmic scales, which just turn multiplication into addition. Okay, so that's everything that we have to do for this chapter. Oh, there's one more thing that I just want to point out. It's maybe not totally obvious, but we can, with these formulas, they go both ways. Remember, we learned about anti-logs. So remember that on your calculator, you may have a button that says anti-log, which is the same. Some of you might have a button that's log minus 1. That minus 1 means inverse. So an anti-log is the same thing as an inverse. And when we're dealing with log base 10, that's the same thing as 10 to the x. So this equal sign with an extra bar is a mathematical symbol for equivalent. So that the anti-log, log inverse, or 10 to the x are all equivalent. And you'll probably have just one of those on your calculator. So I know that the pH is equal to the negative of the log of the h, which means that if I have the pH, I can calculate h. And I just do that by reversing all those steps. So let's say I have pH is equal to the negative of the log of the molar concentration of hydrogen ions. So the first thing I'm going to do, I'm just going to kind of unwrap this H plus by moving everything, doing everything to both sides to undo everything here. So the first thing I got to do is get rid of this minus sign. So I'll do that by multiplying both sides by negative 1. So negative pH is equal to the log of H. And now I do the anti-log of both sides, or log inverse, or 10 to the x. So whatever your calculator has. In the textbook, I think they use the word anti-log. So I will use one of these other ones just so that you see it in a different way. So I'm going to use 10 to the x. So that means 10 to the negative pH is equal to, and remember this just reverses log, so it's just equal to, oops, the molar concentration. Okay. So I'm going to write this out all three ways. So my molar concentration is equal to the anti-log of the negative of the pH, which is also the same thing as saying the log inverse of the negative of the pH, which is the same thing as saying 10 to the power negative of the pH. So depending on your calculator, you'll have probably just one of these. And lengthwise, let's just get rid of all of this. We can do the exact same thing with the POH. So we have these couple of other rules, which are really just restatements of these rules. It's just these, it's this guy and this guy going in the other direction, if you will. So I know that h is equal to 10 to the negative pH, and I know that the OH, so molar concentration of hydrogen, is equal 10 to the negative pH, and OH, the molar concentration of hydroxyl, is equal to 10 to the negative pOH. So these two are given as separate formulas in the book, but they're really just writing these two formulas here in a different way. So we have these two formulas about pH and pOH, and this guy, which is just a restatement of this. And those are the formulas that we're going to use. The next film, or the next YouTube video, will just be using these formulas to do some of the problems in the practice set.